Hello and welcome to this video on similar figures and polygons. Today we're going to be determine if figures are similar by identifying scale factors, comparing proportions, and also looking at some angles on these shapes as well. So you would want to add in angles as part of this too. The vocabulary we're going to be talking about throughout this presentation are listed in front of us here. All of these have been mentioned in prior videos. If you're unsure of any of these videos, please pause the video and use Google to look up definitions to any of these unfamiliar words, as they will be mentioned throughout this presentation. The two problems we see in front of us are review from past video lessons. The one on the left is using the exterior angle theorem. The one on the right is using the triangle sum theorem. Please take a second to pause the video and try to find the answers for X for both of these problems to see how much you might remember from prior lessons. In the two sets of shapes we see in front of us, you are looking at 3 out of the 4 that are similar in some way to the other shapes in front of us, and you're trying to find the exception to the groups that we have in front of us. Now, you can make a case, since we don't have exact measurements for a lot of different shapes, but one easy one to point out is if you look in set number 2, you will see shape C seems to be the only one of those triangles that has a 90-degree angle. We will see later that you need all of the angles of a shape to be the same for it to be truly called similar. So if one shape has a 90-degree angle and the other shapes don't have 90-degree angles at all, well, that would mean for sure that they are not going to be similar. And that is the sort of thing we're going to be looking for. In prior lessons, we've talked about transformations a lot. Now, when you have a rotation, a reflection, or a translation, all of those are known as rigid transformations. After all of those, you would obtain a congruent shape. That means the same size and same shape, all the side lengths and angles would all be equal to each other. Now, when you have a dilation involved, that makes a similar shape instead. It is the same shape, but it is not the same size anymore. And that is demonstrated simply in the picture in front of us, where we have a black pre-image and we have dilated this shape to get our red image in the middle. If we just take a quick second to look at it, if you start at the origin and count over to where point A and A prime are, you would need to count over 1, 2, 3, 4 spaces and then down 4 spaces. If we were to look at how to get from the origin to A prime, that would be over 2 and down 2. So that's half as many spaces in both the X and Y direction. So it seems like this red shape, or black shape, was dilated by half in order to get its red image. To expand upon that a little bit, you could take a second to graph these points in our pre-image and image, and we're going to compare how the sizes of these two shapes in order to see if they're going to be actually similar to each other. So if you compare our blue pre-image to our green image, you can see that across the top of our blue image is 3 spaces, and now we have across the top 6 spaces instead. You can also see that there are 4 spaces compared to 8 spaces. So if you think about new compared to old in what is called a proportion right here, you would see that from larger image, the new one, compared to the old one, 6 to 3, that's double the size. And 8 to 4 for the length is also double the size, meaning our scale factor is equal to 2. And you can see that both of these fractions are equal to each other. And remember, a proportion, all that is just when you have 2 fractions set equal to each other, you have a proportion. Another example here, we only have 3 points making a triangle, and looking pre-image to image to see if a dilation is what happened. So if we compare these two shapes, where we're starting out with this pinkish hue of a color shape, you can see that going up the length of the side, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 spaces. And the orange is 1, 2, 3, 4, 5, 6, 7, 8 spaces. So 8 to 12 would be a 2 to 3 ratio or proportion between the sides of the triangles. But if you compare the other lengths, we have 12 again. We have 12 again, and then we have a length of 9. So that would be a different proportion. We have 2 to 3 and then 3 to 4, which would be a different increase in size. So this would not have a constant scale factor, which is what we want for all dilations that we do. So time for a little bit of notes. Similar figures have the blank shape, but the blank sizes. We would fill that in with the same shape, but different sizes. And the 2 bullet points here are incredibly important. All angles are congruent, all sides are proportional. That second bullet point basically means that I should be able to take any length on my smaller image, multiply it by my scale factor, and get the larger side of the bigger image. And that same thing would work for all of the sides of the shape. And when it says all angles are congruent, if every angle in your shape is the same as its image, that means that they are in fact similar to each other based on that bullet point. And that would obviously mean they have the same number of angles, which is kind of implied. And depending on what shape you're talking about, it might be a square or a triangle, you might know how many total degrees are in it. So you may only need most of the angles congruent in order to tell that they are actually similar as well. We are looking at some continuation of our notes here. And at the top, it reads, 2 polygons are similar if the second can be obtained by the first by a sequence of translations, reflections, rotations, dilations. And that is essentially what we're building off of from our last unit. And that's something to keep in mind as we go. So we're just looking first to just name everything in the correct manner. So we have these polygons below, and these are pentagons with 5 sides. And we have a pentagon on the left, and then one that is similar to it on the right, which is smaller in size. And we can see that we have some angle measurements over here. So we're looking to just kind of line up and what angle would match each one. So angle A and angle P would be congruent to each other if these two are similar shapes. So they are matching letters to each other. Then it would be angle B and angle Q. And then we'd have angle D would match to angle S. And these angles are all congruent if we are being told that the shapes are similar. If we're thinking about sides, there's kind of different ways you can set up proportions, but we'll talk about that in a second. For this first one, AB to BC, the kind of the 2 sides right next to each other, would be PQ and QR. And then continuing on, we got CD and DE kind of right next to each other again. So it'd be RS and ST. And then lastly, if we're going PT and QR, well, QR and BC match each other. So PT and AE would kind of match each other. Some things about proportions that I wanted to add here, though, is if we're specifically talking about this one, for instance, you can see how when you make a proportion, the AB and BC are related to each other on the same shape, and then PQ and QR are the same thing. Another way you could write that same proportion would be with AB on the top of that fraction and BC on the bottom. So they're relating it kind of up and down. And then the same thing, the AB and PQ would be on the top, and then QR would be on the bottom. So you can see that our first proportion had the same shape on the both on the top and then both on the bottom. There are the shapes from the same ones. Now we have them up and down over here. So I could take this and I could also just flip both sides, kind of either upside down or right side up, and that wouldn't change my proportion either. That would be an okay thing to do. But the last thing we will mention here is that something that is not okay is if you have AB on this part over here, and then you had your proportion, you're not supposed to put things that are kind of diagonal from each other that are from the same shape or from the same source. So if I took this and I knew that AB and PQ still match each other, so I could put that there, that would mean QR is over here. If you have things diagonal like this, you're not going to get correct answers. So it's important to remember for everyone that don't have things that are related to each other from the same shape diagonal from each other in a proportion. Now, we've talked about scale factor before, but the ratio of the sides is called the scale factor. So in the polygon above, if AB were 12 and PQ were 8, so from AB to PQ, then the scale factor would be 12 to 8 or 3/2. And then we can see that the symbol we've discussed before in class is this symbol, which is called a tilde. And it's showing that these two shapes are similar to each other. So let's take a second to practice some of these ideas we've just talked about. So we don't have any angle measurements here, but we can kind of see that, well, most of these angles, they kind of just look like it's been translated to the right and then dilated down to be smaller. And so if I wanted to make a proportion here to solve for some of the X, Y, Z lengths that I'm missing, I need to basically set it up in one of those kind of proportional ways from before. So let's go in alphabetical order. So I know that I have my X and my 21 from big to small that are matching each other. So X over 21 would be something I could do. And then I got to find another pair of sides that are also like that as well. So I could set up that proportion from, if I'm doing small over big, I could then do 20 small over big. Now, when you have a proportion like this, there's a couple of ways you could solve a proportion in general. So one of those ways is to cross multiply, where you would do 21 times 20 and then 30 times x. So that would basically, if we lose some colors here, so it would be x times 30, 21 times 20. And then I would take those answers and have them over here to the side. So 420. 420 would be equal to 30x. And then you would just divide by 30 to get the answer for x to be 14. So that would solve for us what x is going to be. But as we kind of saw in our last slide, that we could take big over small and divide and get a scale factor instead. So if we did that instead of just solving a proportion, it would look a little bit differently. So let's start over, and we know that x we just found was going to be equal to 14, so we'll keep that in that answer. But basically, we would just take our 30 over 20, similar to how we did the big over small, 12 over 8. So I could just do 30 divided by 20. 30 divided by 20 is equal to 1.5. And that is going to be equal to our scale factor. And instead of making a proportion, you can just multiply out the things on the smaller size shape to get to the larger shape. So for instance, I could take this 10 right here and I could do 10 times 1.5, and that would give me an answer of 15 and give me the answer for my z right there. And then I could do the same thing. I could do 8 times 1.5, and that would give me that y over here is equal to 12. So keep in mind this can also go backwards. If I didn't know that x was 14 and I needed to go from 21 down to x, I could just do 21 divided by 1.5, and that just equals 14 as well. So that shows different ways to do it. You can set up proportions like we were doing before and cross multiply. You can also determine the scale factor and use that to your advantage as well. Moving along, we have two quadrilaterals, which don't have any other name besides quadrilateral. So we're going to look through and answer A through F in this problem now. So we're going to try to use what we know about similar shapes. All of the angles are congruent, sides are proportional, to determine what we have going on for all these answers. So let's try to do the easiest ones first. So we know that they're similar. So these 90-degree measurements right over here should be able to tell us that we have 90-degree angles at T prime and E prime. And that's actually the answer for question B. Angle E is 90 degrees. So if we go back to question A, we know that U prime is 135. So I know that U is also 135 degrees. And since we are working with a quadrilateral, all quadrilaterals, the insides of their angles, they all have to add to 360 degrees. So if I am trying to figure out my answer here, so I would just basically do 360 subtracting all the angles that I know in the shape. So that would be subtracting 90, 90, and 135. So if you combine 90 and 90 and 135, that is equal to 315. And that would leave us with 45 degrees remaining, which would be equal to angle N. And that would also end up being angle N down here. So they're both going to be 45 degrees, N and N prime. So let's try to figure out the C, D, and E using a scale factor. So we need to do, for our scale factor, we're going to do 35 divided by 28. And the answer we get ends up being 1.25. So our scale factor is 1.25. And we can use that to find the sides that we're missing. We know we have our next first one we need to find is TU. So I can just do 16. I can do 16 times 1.25 to get that answer. 16 times 1.25. And that is going to be equal to 20. So TU is going to be equal to 20. Next, we have T prime, E prime. We have a 15 over here, so we just need to do 15 divided by our scale factor to get the smaller of the pair of sides. And 15 divided by 1.25 is equal to 12. Finally, the missing side that we need is UN. So if our 12 right here is on the small one, we just need to do 12 times 1.25 to get that answer. And that is going to come out to an answer of 15 for segment UN. And if we want to just add up all the sides for the shape we have here, we know we had a 20 up here earlier. So UN we just found was 15. So we're really just going to figure out the how different, what's the scale between perimeter of the bigger and smaller ones. So if we add up all the sides of our big shape, we would have an answer of 85 for our larger shape. And then the perimeter of our smaller shape would end up as 68. And if we do 85 divided by 68, we end up with an answer of 1.25, which is equal to our scale factor. And we've shown that the perimeter also follows along with our rules about similar proportional sides, and it is also proportional. Moving along, we're going to look at some more examples of finding the missing pieces for our triangles here. On this next two problems, we're going to be looking for y, x, and z for these two shapes. So something to keep in mind is some of it contains some things we're going to cover later in the year. So we'll kind of just breeze through past those a little bit here. So if we are looking at this top shape, we know that these are similar polygons, like we've seen already in this presentation. So we want to think about what we can fill in about them. So first, for the fact that the triangles, we know that they add up to 180 degrees. So 60 plus 90 is 150, leaving us 30 degrees left over right there. And so that 30 degrees would match down here. So this would equal to our 30-degree measurement, making this also 60 degrees, this slightly bigger angle up there. Now that we know that, we want to figure out what our scale factors are. So first and foremost, we know that 12 and 20 are matching each other. So I'm going to find my scale factor by doing 20 divided by 12. So 20 divided by 12 gives us an answer about 1 2/3. So we could say it's about 1.66. Or if you don't like that kind of decimal with a repeating decimal on it, we could just reduce this by dividing both of these by 4. So our scale factor is really going to be 5/3. So either one of these two could work for this problem, depending on what you want to do. So if I wanted to get z, I can do 12 root 3, 12 times the square root of 3, multiplied by that 5/3, which I'm going to use 5/3. So if I have that 3 in the bottom, I can divide this 3 and this 12 by 3. So I would have a 4 right here. And that means my answer is 4 times the 5, which would give me 20 times the square root of 3. And that was what we would label our z value down here, 20 root 3. And then lastly, we have our hypotenuse over here, this y. So then we would just do 40 divided by 5/3. And then that would basically be the same thing as 40 times 3/5. And so we can just do some multiplication and cancellation. So I can just divide this 5 and this 40 by 5. So that would make this an 8 and this into a 1. So our answer there would be 24 would be equal to y. We have one more to get to of these type of problems. So we have a trapezoid here where we have some similar shapes to deal with. And so if we think about getting the sides we need, we basically need all 3 missing sides of the smaller shape using the big shape and some different information we have here. So we need to figure out the scale factor first. So I know that the 10 right here represents the bottom of the little shape, and then 10 plus 14 would be 24 is the bottom of the big shape. So I would do 24 being divided by 10, and I know that is equal to 2.4 is going to be our scale. 2.4 times bigger. So now we just basically need to do 15 divided by 2.4, 16, and 12 all divided by 2.4 to get our answers. So we're just doing division here, so pretty straightforward. So I can just do 15 divided by 2.4 and get that x is 6.25. And then I would do 16 divided by 2.4 and get 6.6 repeating. And then finally, I can do 12 divided by 2.4 and get that z is going to be equal to 5. These examples are asking the person to determine if the triangles are similar. And remember, we know if triangles are similar if all the angles that we see are equal to each other and all the sides that we see are proportional. If we can show that, then we would know that they are definitely similar. So we're going to ignore where it says side angle side right there. That's a thing for later on. So we'll come back to that in a later video. So for right now, we can see that we have 9, 18, 12, and then a smaller shape here that is kind of similar to it. So we know that from the small shape to large shape, I can do 3 times 3 to get 9. And so that 3 times 3 to get 9. I can do 6 times 3 to get 18. And I can also do 4 times 3 to get 12. So that shows that all of these matching sides are definitely going by the same scale factor and they are proportional to each other. So in this next pair of triangles, we have a 90-degree angle in both of these. So that's already a good instance that we can look for. So otherwise, if we're looking at some of these shape or sizes of the shape, from 6 to the 4 right there, or from 4 to 6, that from 4 to 6, that is multiplying by 1.5. But if I'm going from 6 to 8, if I multiply 6 by 1.5, that is going to equal to 9 instead of 8. So that would mean that these two shapes are not similar since the sides we have showing are not proportional to each other. For numbers 3 and 4, we're going to approach it very similarly. So we have angles showing in number 3. So if we look at these two shapes, we want to think about our triangle sum theorem here. So if I know I have a 55 and a 53 degree angle, I can do 180 minus 108, that total, and get this missing angle is 72 degrees. Now if we look on the right angle, we have a 55 and a 72. So if that would add up to 127, so 180 minus 127 equals 53. So that means that we have all of our angles are congruent, and we know that these two shapes are definitely similar, unlike number 2 when we determine they are not similar. In number 4, we have a 46-degree angle right here, so that matches up on both triangles. And we want to look and see if our sides are proportional. So from 7 to 12, we want to figure out our scale factor. So we got to do 12 over 7. And 12 over 7 comes out to an answer of about 1.71. And so let's check to see if this is the same scale factor. So if I do 24 divided by 14, that also equals 1.71. So we know that their scale factor is the same, and we have another angle to kind of lock them both into place. So we know that these two triangles in number 4 are similar. Now we can move on to our last two examples. In number 5, we see we have a 54-degree angle matching up here. From 3 to 9, we have a scale factor of times 3. And from 15 to 45, we have a scale factor of times 3 as well. And so that means that these two triangles in number 4 are definitely similar to each other. And finally, we have a 90-degree angle making these both right triangles. And from 8 or 10 to 20, the two hypotenuse lengths, well, that's times 2. But if I go from 8 to 12 over there, well, that is not going to be times 2. That is going to be times 1.5. And that means that these two triangles are going to be not similar to each other.